again, I think this section has a lot of stuff in it. Tests for symmetry, I think you talk about this in geometry class maybe when you talk about symmetric with the x-axis and the y-axis, but then in algebra 2 I don't know how much you talk about it. But testing for symmetry or knowing that a function is even and odd is going to make things a little easier when you're graphing. If you know those things going into a graph, it means you have to do less work to graph it because you know certain things are going to happen. So that's why we do these tests. Today we're just going to kind of practice how do you tell if something is symmetric with a different axis, or how do you know if it's an even or odd function without having to graph it. And then tomorrow we'll get into more with graphing. We're also going to talk about asymptotes today, reviewing those. So asymptotes I know you did in algebra 2. This stuff maybe not so much. So I do these lovely graphs for you because for me I never like memorize this. I just think about what's happening. So if you had something that was symmetric with the x-axis, that means whatever's up here, you flip it over the x-axis, it's exactly the same, right? So like this would be, oh, I should change colors here. So that's a different color. Oh, that would change colors. I've lost control of my... Oh, look, I know why. Look, this is for this one. Or this one to me at this point. So if you flip something over the x-axis, the y value is going to change, right? The x is still at the same spot, but now you have a negative y. And in geometry, I'm teaching geometry for the first time this year in a long time, but I remember the last time I taught geometry, kids would try to memorize all that stuff, and I thought it was just silly if you just visualize what's happening. Oh, over the x-axis means the y is changing. And so down here I kind of summarize it for you. If it's symmetric with the x-axis, if xy is on the graph, so is the point x negative y. And then I got tired and just put the quote marks under there instead of typing it every time. Just kind of silly, but... If it's symmetric with the x-axis, it doesn't pass the vertical line test, right? And so we don't have a lot of x-axis symmetry until we get to second semester and we start graphing some crazy stuff, because it's not a function. But y-axis symmetry, we have a lot of those, right? If it's symmetric with the y-axis, that means it's just going to flip over the y-axis. So whatever's on the x-axis or on this side will flip over, and it'll be the same over here, which means the x is going to change. So negative x y. So those are very good to visualize, I think. Origin symmetry is a little bit maybe harder to visualize, but it's like when it goes from quadrant 1 to quadrant 3. Someone described it last year as like doing it in both the x and the y-axis. Like if you thought about flipping it over the x-axis and then over the y-axis, like that's origin symmetry. Or if you went y-axis and then x-axis, you're still going to end the same way. So that's kind of a good way to visualize it if you're struggling thinking about how I would get like this, right? I really struggle drawing that. Helps me if I make noises when I draw it. So it would like flip over and then flip over again. And that means both the x and the y are changing. So negative x and negative y. Obviously, if you have a graph, you can just look at the graph to see if it's symmetric with these axes. But what we want to do is be able to do that by just looking at the function and maybe even coming up with some quick ways to do it. And also talking about even and odd functions go right back to the symmetry here. All right, so let's just practice doing this, and it's kind of just some algebra stuff that we're going to check. Sometimes you're going to be able to do this in your head, if that's okay. I just want to show you how to do it if you were going to actually work it out each time on this problem. So it says use algebraic tests to find symmetry. So I'm just going to write it out here. We're going to test the x-axis, the y-axis, and the origin. And what you want to think about is if xy is on the graph, will those other points be on the graph too? And so I'm just going to write them out kind of like what we just wrote on the previous page. But for x-axis, we said if xy is on the graph, when you flip it over, the y changes, so that means x negative y is on the graph. So a really easy way to check for symmetry is if you plug in this point into the equation, it should simplify back to be what it started with. Like nothing should change if it's symmetric with the x-axis. So I'm going to show you what I mean by that. So x is obviously going to stay x. But if I replace y with negative y, if it were symmetric with the x-axis, then what I end with should be what I started with. If they don't look the same, then it's not symmetric with that. And again, I understand you're going to be able to do that in your head. You're going to be able to say, well, negative y is going to change the sign of y, so I know it's not x-axis. But I just want to show you where it's coming from right now. So I'm going to say no. For the y-axis, we said if we plug in a negative x and the y stays the same, right? That's symmetry with the y-axis. And again, I know you're going to be able to kind of look at that and know what's happening, but I just want to show it to you in the notes here. So if I replace x with negative x, and I leave y the same, right? It's really nice because it's x squared. When you square a negative, it's the same as it just being a positive, right? Because negative x squared is just x squared. So since this is exactly what I started with, that means yes, it is symmetric with the y-axis. And you probably already know the answer to the origin. Remember, the origin was both of them changed, right? Gotta be careful sometimes doing this in your head, because sometimes you think, well, the x didn't work and the y didn't work, there's no way this one can work. But sometimes it'll cancel out if they're multiplied together, so just be really careful on that one. But I think this one doesn't work because the x is going to stay the same, right? But the y is going to change. So we get x squared plus y equals 0, which also is a no. Next semester, when we talk about symmetry with non-functions, like circles or rose curves, like awesome things like this. Oh, that's a pretty graph, right? They can be symmetric with all three, actually. Some graphs will be symmetric with both the x-axis, the y-axis, and the origin, depending on how it's drawn. That's not till like April, so we got a ways to go. Talking about our functions now that we know, probably it's going to be one, maybe two, but probably not all three. Questions on how I did that? Definitely there'll be a question on the test that we have for chapter 1 asking you about symmetry. Is it symmetric? All right. The other thing that goes right with symmetry is even and odd functions. Even and odd functions are actually just talking about symmetric functions. So even functions, I left some blanks here for you to fill in. An even function is a function that is symmetric with the y-axis. Maybe my favorite, most famous even function that we deal with all the time is f of x equals x squared, right? It's even because if you graph it, it is symmetric with the y-axis. Any parabola that's centered on the y-axis there, wherever it is, you could fold it over and it would be the same. So you could use the same thing we did before where you plug in negative xy, it works. Another way to write that is we can say if you plug in f of negative x, you should get back f of x, which is exactly what we just did, just writing it a different way, kind of using function notation to do that. And so we'll talk about that in a minute with an example. But that works, right? If I plug in negative 2, I get the same thing as when I plug in positive 2. Really nice if you know a function's even, because if you graph one side, you don't have to pick points for the other side. You just know it's going to be the same. So that's why we like knowing that. An odd function is a function that is symmetric with the origin. Is that fancy font I use there? And hopefully, maybe you know an odd function off the top of your head is x cubed. Maybe not as familiar with x cubed as x squared, but x cubed also starts at 0, 0. When you plug in 1, you get 1. When you plug in 2, you get 8, right? It goes up very quickly like this. But it's not even, because when you plug in a negative number and take it to the third power, it's always going to be negative. But you're going to get the same thing you got going up, only going down. So then it kind of turns like that. Odd function. So by definition, when you plug in a negative number, you get a negative y value. So when you plug in negative x, you get a negative y value. So f of negative x equals negative f of x. And I have a few examples here, and I actually feel like they're kind of out of order because 2 is always the one that confuses everyone. So we're going to skip it first, and then we'll come back to it at the end. It's all on the same page here. But even and odd functions, just another way of talking about symmetry here. And when we talk about new functions that we're going to learn about this year, especially trig functions, we're going to talk about if they're even or odd, because it really does make graphing easier if you know that. All right, so let's go out of order here. Let's skip 2 for a minute, and we're going to do 3 and 4 first, and then we'll go back to number 2 here. Is it even, odd, or neither? Because it might not be either one. An even function, I'm going to shrink this over here, means that when we plug in a negative x, we get back exactly what we started with. So the negatives kind of just all go away. If it's an odd function, when we plug in a negative x, what we should be able to do is factor out a negative, and everything else stay the same. So it's like it changes the sign of everything, basically. If it's somewhere in between, like a few things change sign and a few things don't change signs, it's neither, right? It's not even or odd. It's somewhere in between, right? So that means it's not symmetric with the y-axis or the origin. And there's a lot of graphs that aren't symmetric with any of those. So a really easy way to check is plug in negative x into your problem and see what happens. So I'm skipping number 2 for a minute. But if I plug in negative x here, and it's okay to go ahead and simplify if you want, but again, sometimes I think showing more work in your notes is helpful for when you go back and have no clue what happened. You're like, I don't know how I got here. Negative x squared, that's just going to stay x squared. 2 times negative x is going to change to minus 2x, and minus 3 is going to stay minus 3. So if it's even, everything should look identical to what we started with. If it's odd, everything should be the opposite sign. If it's somewhere in between, it's neither. And so number 3 would be classified as neither, right? Because this changed, this didn't change, this changed, this didn't change. It was neither. And think about most parabolas. Like if it's a parabola that's not centered at the origin, moved off somewhere, right? It's not going to be anything. What about number 4? Do you know the answer to number 4 without doing all the work? Right? When I take an even exponent to a negative number to an even exponent, it's still going to be a positive number. So I say number 4 is even. Do you think you could think of a rule that would help you find an even function really easily? Did you notice anything about on number 4? Yes? Yeah, the exponents are all even, which means when I plug in a negative number, like it's going to stay the same. So it's not a coincidence that all the exponents are even and I got even as my answer. They could throw something weird in there, but for the most part, right, that's gonna work out. exception to that would be, well, no, that wouldn't work. That would work too. So yeah. Yeah, I think that would work. All right, what about number 2? If I plug a negative x in there, I'm going to get negative x out front. And then in here, that negative for the x squared is just going to go away, right? It's just going to stay 1 minus x squared because the negative is going to go away. It's definitely not even because we have a negative out there. My question is it odd or is it neither? Or are you unsure? Yes. It is odd because we could just pull this negative, right? Like we could write this as negative x times the square root of 1 minus x squared. People struggle with that because, I don't know, I think we forget that this is multiplication, so if you pull the negative out, you only pull it out once. Like, people think that should change the square root somehow, but it doesn't. So that one negative comes out front, and what's left is the same, which makes that an odd function. So sometimes these are very straightforward. Sometimes you might have to think a little bit about them to do them. But just know that even odd or neither, like, it could be one of the 3 answers there. And again, you'll definitely see that again. Okay, so I've never printed these notes out before, but I don't know why I decided to this year. But the next slide always throws people off, especially when you're writing your own notes. You can see this big ugly thing for a rational function. When we're talking about domain and range, rational functions always come up because they rarely have a domain of all real numbers. And so this is the math way of writing a rational function. Don't get freaked out by it. It's just how we write rational functions when we're just talking about letters. So it just means like starting with the highest exponent, and then usually we write them in descending order. So think about something like this, like 2x squared plus 4x minus 6. That would just be your leading term with your highest exponent, and then usually we go down by 1, and it could have like tons of things, which is why we say dot, dot, dot. And then it ends with x to the first power, and then your constant, which they're just calling a sub 0. The bottom has some other expression in it, and they just use b there, and they use x to the m, so it could be like 3x cubed minus 4. That could be like that, right? And so it just, again, normally starting with the highest exponent to the lowest. Writing the rules for horizontal asymptotes, I think, is easier using this notation. And again, being in pre-calculus, I'm going to use the real math notation more than just trying to skim over the math talk, because in pre-calculus, I think you should get the math talk, all right? So, some numerator function, some denominator function. There are 2 types of asymptotes that you learned about in Algebra 2. Vertical asymptotes are what we were just doing on the homework from yesterday. What x can't be, right? What makes the denominator equal 0. So, vertical asymptotes, all you have to do is find the zeros of the denominator. So, set denominator equal to 0. If nothing makes the denominator equal 0, that means there's no vertical asymptotes. If you know your domain, then you probably know your vertical asymptotes. If you know your vertical asymptotes, you know your domain. Horizontal asymptotes are a little bit more complicated. And for us, we're never going to deal with a function that has more than one horizontal asymptote. So there's either no horizontal asymptote, or there's one horizontal asymptote, and there's 3 options here. It all has to do with the degree of the numerator and the degree of the denominator, which is the highest exponent in the numerator, the highest exponent in the denominator, which is why I wrote it like this, so we can just use n's and m's here. All right, so if the numerator is less than the denominator, that means, just like yesterday, y 1 over x, that had the horizontal asymptote of y equals 0. So if the degree of the numerator is less than the denominator, then your asymptote is y equals 0. Oh, it already appeared again. So that would be like y equals 1 over x. That would be an example of that. If the numerator and the denominator have equal degrees, you have to take the leading coefficients. And again, this refers back to up here. So that means there could be anything. It could be any number. So if I have something like y equals 4x squared minus 6 over 3x squared plus 1, because the degree of the numerator is equal to the degree of the denominator, my horizontal asymptote would be the line y equals 4/3. Right? Asymptotes are equations, so always make sure you write it as an equation, not just as a number. Like, don't just say 4/3. Say y equals 4/3. And then the last option, if the numerator is bigger than the denominator, there is no horizontal asymptote. And last year, you actually learned about slant asymptotes, and we'll talk about those later, but not right now. So right now, we're just talking about vertical and horizontal. So if the degree of the numerator is bigger than the denominator, like x squared over 1 minus x, right? 2 is bigger than 1, so this would have no horizontal asymptote. Memories of that from last year? So those rules, you just have to know them. There's not really a shortcut to it. Like, that is the shortcut. Okay? So again, today we're not graphing these. Today we're just going to practice finding asymptotes, and then tomorrow we'll get into to graphing those. Okay, so let's just do a couple of these, and then I'm done. So actually, I'll just be quiet for a minute and see if you can use those rules I just gave you to find vertical and horizontal asymptotes of these two. So there's no need to label them as vertical or horizontal, because when you write them as an equation, you should be saying x equals or y equals, and so that tells you which way it goes, so you don't have to tell me which one's vertical and which one's horizontal. If you know the rules for horizontal, I think it's easier than doing vertical, because vertical you actually have to do some math sometimes. But a lot of us tend to start with vertical because we're comfortable with saying, I know, I just have to figure out what makes that equal 0, right? So the domain would be that couldn't equal 0. My asymptotes would be, where does that equal 0? So I believe that there would be two vertical asymptotes, right? X equals plus and minus 3. So vertical asymptotes are equations. Where does the denominator equal 0? What about the horizontal asymptote of this? What would the horizontal asymptote be? What's the degree of the numerator? 1. And what's the degree of the denominator? 2. So 1 is less than 2. So the numerator is less than the denominator, means what is my horizontal asymptote? Y equals 0. Right? You just have to know those rules. The bottom one here, if I set the denominator equal to 0, I get x equals negative 1/2. What about my horizontal asymptote? little reminder about degrees. Remember, degree doesn't necessarily mean the first number. It means the highest x in each one. So it doesn't have to necessarily be first in this one. Neither one of them are first. But both of those have an x to the first as the highest exponent, which means the numerator is equal to the denominator. So you have to use that rule where you take the coefficients in front of that, right? So it's not 1 over 1. It's the coefficient in front of that highest exponent. So you should have said negative 5/2. Questions about that? You are doing 48 through 62, even 74 through 76. I know there's a question that has like an exponential in it, I think, or log or something. Think about if you can remember how you graphed those last year, or maybe even look in your book. Chapter 3 has those in there to remember what they look like, and I'm sure we'll talk about it tomorrow. But again, you don't have to graph these. Tomorrow we'll talk about graphing them, and I think I'll have a worksheet for you tomorrow because the assignment sheet doesn't have anything for this, but I think it just kind of reiterates the asymptotes by doing this. I'm also passing back your homework.